Hello, and welcome to the ROSA Worldwide Webinar Series. My name is Mike Reed. I'm the Chief Scientist at ROSA and your host for today's webinar. Please check the ROSA website for the upcoming webinar schedule. These occur monthly. If you would like to submit questions for the speaker for today's webinar, there is a button at the bottom of your screen that says Q&A, and you can click on that and submit your questions. The speaker will answer those at the end of his presentation. Today's speaker is Wojciech Krzyzanski. Dr. Krzyzanski received his PhD in applied mathematics and an MA in pharmacology from the University at Buffalo. He's currently a professor in the Department of Pharmaceutical Sciences at this university. His research interests include computational pharmacometrics, PKPD systems with delays, and modeling drug effects on cell populations. He's published over 120 articles in peer-reviewed journals and contributed 3 chapters. He currently serves as an associate editor for the Journal of Pharmacokinetics and Pharmacodynamics, and is also a fellow of the International Society of Pharmacometrics. Please join us in welcoming Dr. Krzyzanski.
Thank you, Mike, for this introduction, and thank you, Rosa, for giving me this opportunity to present today's topic. And the topic of my presentation is application of distributed delay differential equations for modeling absorption delays. Before I move to the actual objectives of this presentation, I want to present 2 examples, motivating examples. And I'll start with the example that is probably of one of the first applications of distributed delays in pharmacometrics. This example is the effect of glibenclamide that was administered to 2 subjects orally. And you see the data on the left from 2 subjects as symbols, and then this data shows a very profound delay or lag time before the onset of the absorption, and then followed by the elimination. And then the dotted line is a line that was obtained by fitting this data using classical lag time model when there was an absorption part, a dosing with was a lag time, and there was the elimination part described by one compartmental model. What these collaborators did was replacing the lag time by a series of transit compartments, as you can see here, and they were motivated because of this not exactly rapid increase in the onset, but more like a smooth transition. And then they refitted the data with these transit compartments, and then the solid line shows you the fittings. So there's a huge improvement in the adequacy of the description of the data by applying those transit compartments. And the paper that I have in the bottom is actually about addressing the issue how many transit compartments supposed to be selected for describing this absorption delay. So I use that example because when you code this model, when you have the sequence of transit compartments, you end up with the input to the absorption compartment being described by this function. This function is actually a gamma probability density function with the integer shape factor, and the purpose of this paper was actually to try to estimate that integer number. So to estimate that the number, they actually at that point, because they couldn't calculate a factorial for real numbers, they make this Stirling approximation, and they used n as a parameter in the model, and they actually estimate the number of compartments. So that was the purpose. My point to this is that you can pretty much code this model using the solution to the last transit compartment being the gamma probability density function, and then you can write your equation for the absorption compartment using that gamma probability function and just follow with additional compartments of the model. So this is the applications of the distributed lag time model or distributed delays model in pharmacometrics following just single dose. Second example I have is the example of paliperidone that was administered to schizophrenic patients in series of clinical trials, and the data was published in this paper at the bottom of the screen, and for various dosing regimens following oral single dose or injections of single dose and multiple doses. And then if you look at the data, you will see this onset that accounts for the absorption, which is not exactly smooth monotonic function. It has this little bump in these yellow dots. When you look at the lag time, it also is not, it is more like a S-shaped type of profile. So that motivated these authors to come up with a quite complicated distribution of delays that basically is the mixture of two weighable probability density function that was coded this way, and that input is inserted into the central compartment by calculating the derivative of that mixture, and then elimination is the only disposition part of this model. So that shows us two things about our modeling absorption, that the absorption profiles might be complicated, not just because of the prolonged lung tight, but also some weird, sometimes double peak, sometimes profiles like this shapes. Therefore, there is need for more flexible profiles to model such data. So that actually is the underlying reason I want to give you an introduction to some tools that have been developed recently in pharmacometrics that pretty much apply similar complex absorption distribution, but using slightly different numerical tools. So I just come up with this diagram when to explain how these tools can be introduced, and basically the way these absorption delays are introduced currently is by having those dosing regimens, which I denoted by this dose input rate, and then there is some functions describing the distribution of those lag times of those delays. And then that feeds as an input to the absorption compartment. And then eventually it gets to the central compartment with just one elimination pathway, or there might be some peripheral compartment, which I call the disposition model. This absorption compartment is something that is optional in the presented approaches. In the approach I'm about to show you, the absorption compartment is actually the key part, and then it has to be there. So I model it using this notation, those delta functions that you see, those are bolus doses, those are direct instantaneous inputs to the doses to the system. And then I use this L notation for the probability density functions. And as you will see, if the doses goes to the enter the model equations as dosing events. So then the delays enter the absorption compartment as probability density functions for the distribution of those delays. And then if you have multiple doses, each of those probability density functions has to start at the time the next dose. And the disposition part of the model is just standard compartmental mammillary model with central compartment with one or none peripheral compartments. So for that setup, if you have a ODE-based pharmacokinetic model, I would like to introduce a technique that will, in a way, simplify at least coding those equations, and may have some other advantages. So to do so, I need to revisit the properties of the convolution integral. And so I started with the definition of the convolution integral. You see it in the first line of this slide. Basically, this is the integral of two functions. That one function comes with the delay, another one doesn't, and the integration is from 0 to t. And the property of that integral is that actually you can switch the order of the functions, and you end up with the same integral value. Another thing is if you convolute the bolus doses with the probability density function, or any function for that matter, it will basically introduce that dosing events as delays to that function. So therefore, you can have this input that I have in my ODE models with those delay probability density function written as convolutions of those dosing rates in terms of the boluses with the probability density functions, the convolution integral. I think the probably most important part of the property of the convolution integral is that you can actually solve the absorption compartment absorption model by using convolution. So it is the convolution of the input with convolution of the disposition function. This is this unit response function, and that is actually a solution written in terms of the convolution integrals. So you will have two convolutions here. When you do that, then you can actually write your differential equations for the central compartment in terms of this convolution notation, which I'm doing in this line. And I do it just to use this property from the top. When you basically switch the order of the exponential with the probability density function, and then you can write it in terms of the convolution of those input with this unit response function for the absorption compartment. And that is a solution to the absorption compartment when the doses goes directly to that compartment with no delays, and actual delays is applied to the output from that this absorption compartment. So that pretty much allows me to introduce this diagram, which basically formalizes the previous slide. I have an absorption compartment with the dosing inputs with no delays to it. And then what happens is the output from that absorption compartment is delayed, and that what enters the central compartment. So this mathematical trick allows me to do two things. First, introduce just regular absorption compartment when I can apply the dosing events to it with no delays. Second thing, I introduce a convolution of this absorption state with the probability density function of the distributed delays. And when such a convolution integral is present in the equation, then the system of the equations that I present you becomes the distributed delay differential equations. So that mathematically and numerically is entirely different system that can be approached from different numerical and mathematical perspectives. So my point of this is when you have some software, some programs that can solve distributed delay differential equation that can tremendously simplify coding such models, and that basically look like ordinary differential equations with this little caveat that you have to have these convolution integrals in them. So that actually brings me to the objective of my presentation, is to show you how to implement such distributed delay differential equations to model absorption data using solvers that support such tools. And pharmacometrics, currently we have two programs that do that. One is Phoenix, and I will show you how to use the function delay that calculates the convolution integral. And another one is a non-mem 7.6 that has this sequence of library models, advanced starting from 13 up, and I will use one of them, advanced 16, that supports solving distributed delay differential equations. And then I will do that basically by setting up some simple ODE model. Then I used to simulate some absorption delay data using R software, and then I basically did it for just one subject, and then I just refitted the data using ODE and DDDE models in both software programs, and just to show you how to do it and show you how much the differences between those two models were. So to be able to explain the additional features that are necessary in coding and of those distributed delays, I really need to provide some basics, at least in the notation, and some features of the distributed delay equation. So I just presented you with this general structure of this distributed delay differential equation. This is a system of differential equations in a vector notation. So it has this right-hand side that depends on some input, time-dependent inputs, the state themselves. General distributed delay models also allow presence of the discrete delays, which I'm not going to talk about. But the key feature is that at least one state in such system has to be convoluted with the probability density function for the delays, and I call that function the delay kernel short. And then if such state is present with those convolution, the convolution integrals requires knowledge of the states, not the times that goes on after the first dose in the future, but also the value of that state before that dose was given. So in our situation, almost always there is no drag when first dose is administered, so the past conditions are trivial. Basically, this is zero, but you might think of some protein drugs with pretty much mimic the pharmacological effects of endogenous hormones, and in that case, this might be quite often presence of some constant endogenous levels of that drug. So this past condition is required for the distributed differential equations model, and it has to apply for all negative times. So that would be an additional feature of models that are not present with ordinary differential equations. Instead, the initial conditions will apply to those states that are not delayed, and then they are just standard part of the ODE models. So we will need to always look up for such implementations for some syntax, some objects that account for the convolution integrals. And we will need to always know what would be the way to determine the past for those delayed states. Another thing I want to explain for the simulations, I use the Weibull function for the kernel of the simulations, and the Weibull function has this is the equation for it. The probability density function has two parameters. One is the shape factor. This is the factor that is the power this exponent here, and then I use the notation for my model equation that uses the rate, but actually the most common in statistical software and statistical literature is the notation when they use the scale parameter rather than rate parameter. So when you apply those functions, please pay attention to what type of parameterization those functions are using. So you can have a difference between rate parameter and scale parameter. Scale is basically the reciprocal of the rate. And then I just provided for your reference, and we will need that as well in our codes, the value of the mean of the Weibull function, and this gamma function. This is this Euler gamma function that is the special function that most software supports those days. The first slides I show you, the Savage paper, that gamma function was not the supported at that time, and basically gamma is just extension of the factorial function to real numbers. So I plotted three profiles of this Weibull distribution function. Depends on the shape factor. When shape is less than 1, so this red line, that distribution becomes singular at 0, so this graph goes to infinity. When shape factor is 1, so that basically reduces to exponential distribution. And then when the shape factor is greater than 1, it has this unimodal shape with one mode and then right tail that extends to the infinity. And this is the shape factor that I use for simulation, and I use the value of the rate or scale, because it is 1, it is the same value for simulation of the data. So this is the summary of the equations for the ODE model and DDDE absorption one compartmental model using the notation with the Weibull function. So as you can see, this part has to be coded in software by the user. We can use some intrinsic function for the Weibull, but those delays have to be basically typed in. Whereas for the distributed delay absorption model, we can use built-in features for the dosing event. So I have that bolus doses as a part of the input for formal reason, but most pharmacometric software do not require coding that. It comes as a dosing event, and the dosing times are part of the data file. So the program actually knows how to introduce those inputs. So basically, we will code the distributed delay absorption model as a regular compartment model, but there has to be a convolution part that of that program that will be able to calculate this convolution integral with the Weibull function. And I have to stress again, those models are different in terms of the distribution part. When it comes to solving the central compartment model or peripheral compartment models, if they are identical, they are mathematical equivalent, and that was the purpose of my introductory slides. So the concentration of the drug in the central compartment will described by the ODE model, and the DDE model will be exactly the same. Both. So I simulated used the software, the R package DE solve that has the ODE solver, and I used the built-in Weibull function in R, and I basically use this ODE model with those different dosing times to generate single subject data with the doses of 100 milligram of some arbitrary drug at 3 time points, 0, 24, and 48. And then I have this dense sampling times for observations to pretty much make this data very dense and not to create any issues with sparseness when it comes to fitting this data and estimating the parameters. The only thing I wanted to mention is that the scale factor for the Weibull distribution, or any distribution for that matter, I set to be equal to the absorption. If I wouldn't do that, I would have some identifiability problems, and then I don't have time to discuss it today. But basically, this reduction of model parameters is actually required to be able to estimate the shape, the rate parameter or scale parameter of the distribution. So basically, I'm using the absorption rate as a rate parameter, and that pretty much resolves the issue with the identifiability of that second parameter of the delay distribution. So these are the parameter values that I use for simulations. I set bioavailability to 1, so I will not estimate that based just on this oral data. And then I implemented this model first in Phoenix and second in NONMEM. So the next slide will show you how to do it in Phoenix. So I mentioned already the function, the delay function that is available in Phoenix. This delay function has two arguments that always have to be there. So this is the state, S is the state that has to be delayed, either by discrete delay or the distributed delay using some kernel, delay kernel. And then the first parameter is actually the mean delay time. This is the mean value of the distribution of the delay. And other factors, if they are not provided, other arguments if not provided, so there are some default values. But then I would recommend always, providing them. When you use distributed delays, you have to provide the shape parameter for that distribution. You need to provide the history in terms of the absorption delays. That history is 0, so if you skip that is something that is harmless. But then if you don't provide that distribution, the name of distribution option, then the default distribution will be gamma distribution, and you might switch that to other distributions. In our case, that would be Weibull distribution. So the available distributions for the delay function in Phoenix are gamma, Weibull, and inverse Gaussian. Those are just those three. And then when it comes to the output of this delay function, it is presented here. It's not the exact convolution integral that I showed you in the beginning. This integral goes from 0 to the infinity, whereas I show you the integral that goes from 0 to t. But when the history is set to 0, so the value of the state above that, when the tau is greater than tau, becomes 0, so that integral is actually reduces to the convolution integral that I show you. So when the history is 0, the convolution integral from the output of the delay function, the convolution integral I show you are identical. So this is exactly our situation. There is more properties of that delay function, and there are some examples and additional definitions that I skipped here that you can find in this online resource from Phoenix. And I also would recommend strongly, if you want to learn more about implementing distributed delays in Phoenix and actually learn more properties of those models, this is a tutorial written by the Certera colleagues in 2018, and you can refer to that publications for more information. So these are the codes I come up with. I apologize for my crudeness in terms of how I code it, but then pretty much everyone who would apply Phoenix would have to do it one way or another. So the ODE model requires coding these 3 dosing events using the Weibull distribution. So I use built-in Weibull distribution function in Phoenix. This function is parameterized in terms of the shape and scale parameters. So I use the reciprocal of the absorption rate as a scale, and I have 3 doses at those 3 different times. So this is very simple code. I have 2 compartments. This is the absorption, the central compartment, the concentration of the central compartment is my observation, and I basically will estimate just the typical value of the parameters. So this is basically a single subject or naive pool data. That's what I used in this case, estimation exercise. When it comes to the DDDE model, so I don't have to code those dosing events individually or manually. I use the delay function when I have this mean value of the Weibull distribution, and then shape the parameter, and then I specify the distribution as Weibull. History is omitted, meaning history will be assumed to be 0. And I use the equation for the mean value for the Weibull distribution from the previous slide, using not exactly the gamma, Euler gamma. Instead of Euler gamma, there's a function which is the log of Euler gamma. Then if I apply the exponential to the log of Euler gamma, I will actually get the gamma function. So this is a little bit convoluted equation for the mean value for the distribution. And then the dosing events actually come from the data, and this dose point indicates what compartment. So the information about the dosing times and the dose values actually is part of the data you don't see in the model, as you will normally do in most of the pharmacometric software. So in that sense, this notations of the delay that stands for the convolution integral actually is much easier to code than using 3 separate and delay input events coded manual. So I basically fitted this model, both models, to the data, and then, as you can see, the fitted curves are almost identical. They are hardly different numerically, which I checked. Actually, they differ by a second or third digit. Actually, the reason is that the estimates of the parameters coming from ODE model and DDE models are very close to each other, which they actually should, as long as these models are mathematically equivalent. So that pretty much confirms, my derivations from the beginning. So I use the stiff ODE solver, which I will comment on in the end of my presentation, and I basically use this naive pooled estimation that is available for fitting individual data in Phoenix. So that would be the part regarding Phoenix. When it comes to implementing the distributed delay models in NOMEM, there is more logistics than just using regular non-mem code. The reason is that the non-mem actually ask users for additional choices, so that non-mem would know how to calculate the convolution integral. So there are several ways of calculation of convolution integrals in non-mem, and I will refer you to that tutorial that I wrote with Bob Bauer last year. And then I definitely recommend, based on my limited experience with those models, using the quadrature methods of calculations of the convolution integral. And then to do so, the user would have to, first of all, invoke in the code this DDD expanded utility by providing this statement, DDE. And then for the quadrature method, the user need to provide the number of quadrature nodes. And then you need to specify an algorithm by which those quadrature method calculates integrals. It is optional, and if it is not, the default quadrature method is Gauss-Legendre quadrature. But then there are 2 more quadrature methods that can be specified. So this LGY, ALGY variable provides that. When you want to specify the kernel of the distribution, delay kernel for the distribution, you provide this parameter with distribute, and the y is an integer. It goes with 1, 2, and so forth. Basically, if you have one convolution integral, y becomes 1. If you have more, then y would have subsequent integers corresponding to their number. But I haven't done more than 1 yet. And then this example I have for you is also have just one convolution. So y becomes 1. And the path is provided using this APG variable. X stands for the state that is supposed to be delayed, and y is the number of convolutions that you have in the model. And the actual convolution integral, it is denoted by this ADG X and Y variable. So you need to look out in your code for APG, ADG, and introducing those preliminary statements. And one more important thing, when you run such a non-man control stream, you cannot just run it as usual. You have to provide at least one additional argument, and that required additional argument is minus DDE, following your name of your control stream and name of the output file. If you don't do that, then basically non-mem would not apply this DDE expand utility, and just regular solvers will be used, and then syntax errors will show up just because your code will have some DDE related symbols in it. And then there's another optional but helpful in terms of the translating that to Fortran routines, this PR default symbol that basically speeds up the compilation process. So with that introduction, I wanted to just add two more comments. One is about the selection of the delay kernels in NOMEM. So pretty much gamma, Weibull distributions are there, log normal distribution, inverse gamma, but there are some other probability density function that, at least in theory, can be implemented in these distributed delay models. I have no experience with those. But then you can go to this NOMEM users guides that I provide the link to, and then you can read in this section I-35 about them. When it comes to solving those distributed delay models, my personal preference is advanced 16, just because this is the discrete delay differential equation solver that is implemented for solving DDEs. That is stiff, and it has additional features that I don't want to go into that make this solver to be stable in terms of the numerical issues that come up with dealing with delay differential equations. But there is some additional advance you might be familiar with, like advan 9 or advan 13 that I will use for solving ODE model that are also able to solve delay differential equations and can be used for implementing distributed delays. So these are the NOMEM control streams that I come up with to basically code our models. So on the left is the DDE model, ODE model. On the right is DDDE model. And then there is nothing unusual about the ODE model, regular structure. The only advanced feature I would say is this Weibull function that I will use the built-in function in Weibull in NOMEM to calculate this delay Weibull inputs, which are coded using this if statement. The only thing I wanted to point out is that Weibull returns negative log of the Weibull PDF, so you have to kind of convert it back. Excuse me. And then it is again scale in terms of the parameterized in terms of the shape and scale. So I have to invert the absorption rate to provide the correct scale parameterization of the Weibull function. And then those delay inputs are introduced into the equation for the first compartment, absorption compartment, and the central compartment is modeled as usual. And then I use first order, zero order estimation methods. This is individual data, so zero order and first order are equivalent in that case. When it comes to the distributed delay model, then this really have to approach with caution, because these pre-statements before the regular non-mem control stream starts are required. So this is this semicolon DDE invokes DDE expand utility, number of nodes for the integration method, specifying what would be the kernel, and then I also specify the actually default the algorithm for the integration, which is this Gauss-Legendre integration algorithm. And as I mentioned before, you can only use the solvers that support distributed delays, and I use advanced 16. And then the code is pretty much, excuse me, the code is, as usual, a non-man code, but then you have to provide the arguments for the Weibull function, which I've done right here. You have to specify the past, which is 0. So this says this first compartment, the first distributed delays will have the past equal 0. And then the actual convolution integral is modeled as, is coded as ADG, first compartment convoluted with the first distributed delay times. So these are the new features that are not present in regular ODE non-mem codes. If you don't have them, then basically these implementations wouldn't work. And other parts are exactly the same like for the ODE model. So I fit in the same data using those two models. And then the fits again were almost identical. And then the reason being that the estimates of the model parameters were very, very close. So the only difference from the Phoenix is that the NOMEM estimates the variance of the residual error, not the standard deviation. So in that case, this number should be close to 0.001, not 0.1. So don't consider that as a big difference. And as I mentioned, I use first order approximation estimation method to do that. So that pretty much concludes the presentation in terms of how to implement ODE and DDDE models in those two programs. And I want to basically summarize this presentation discussing pros and cons of using those models, modeling absorption data. So I need to stress once again that although mathematically and mechanistically, those two models are different, but they differ up to the input part. The disposition part of those models are described, they are identical. So the values of the amount and concentration in central compartment and peripheral compartments with those implementations are mathematically equivalent. The biggest disadvantages of the ODE models, and this is what that prompted me to give that presentation, is that when you code those ODE models using ODE solvers, you have to manually type in the complex, sometimes, equations for those distributed delays. And that is okay when you have a single dose, and I think I probably wouldn't recommend that. But then if you have multiple doses, you will have to code those, not just those distributions, but the delay distributions with those dosing events. And then that becomes very, very frustrating when you have steady state data, when it's typically modeled by coding quite a big number of those dosing events till the steady state is reached, and that becomes troublesome. So I experienced that, and that's what I come up with this idea. Why would I do this when I have some solvers with distributed delays? Those multiple dosing events pretty much becomes now not an issue. So that's exactly what is the added value of those distributed delay models. When you have the convolution integrals built in, and then if you make this little change in the sequence of dosing events versus the delays, then you can use those distributed delays as I showed you, and use the multiple dosing events as a feature of a solver that is relatively very easy to do because it comes from the data, no coding required. The biggest advantage of ODE models is that basically you can have them in any software that supports ODE solvers, whereas the distributed delay models can only use those programs that can calculate convolutions integrals in them. So these programs are few, and my hope that more pharmacometric programs will add those additional tools to them so pharmacometricians can use them. And then another huge advantage of ODE models over the distributed delay models is the runtime. I just have single subject estimation exercise, but even with that exercise, you can see the runtimes for ODE models in matter of few seconds, whereas for the DDE models, it takes less than a minute, but then 10, 20 seconds, that's what you can see. So the runtime for DDE models is expected, and the reason is just because the DDE models is actually integral differential equations. So the solvers don't just solve differential equations, but they also have to do the integrations in them of the integrals. So that really cannot be faster than an ODE model. So they will always be slower. And then both models, when you have this complex functions for the absorption delays, are really prone to the stiffness in very unexpected parts of the code and part of the numerical execution. So I strongly recommend using stiff differential equation solvers for modeling data with this complex absorption. So with that, I will conclude my presentation, and I'm happy to take any questions.
Thank you. We do have some questions from the audience. First one, is there anything tricky about the data set setup for using these models, like using rate equals -2 or any other special coding?
No, actually not. In the first one is actually when you code those inputs itself, the data set that they don't even have dosing events. So if you have multiple data, basically there won't be any doses coming in because that will be part of the dosing events. So information about dosing times and the dose amounts is part of the code. So the data sets for such models are actually simpler. So in terms of the data sets like normal, when you have the dosing events coming from the data set, they are exactly the same like for any compartmental model. So there's nothing tricky about it. And if you have the infusions, then you have those infusion rates column, and then you inform it. If you have just boluses, you have just boluses, and dosing, there's nothing tricky about it.
Thank you. Next question. It appears that a Weibull delay kernel was used in the case study. Do you have any recommendations on how to select an appropriate delay kernel, especially with respect to biological plausibility, model performance, and parameter identifiability?
This is a great question. Thank you for that, and very often asked in terms of the selections of most adequate mechanistically or pharmacokinetically delay kernel. As you saw, this absorption profiles are really very determined basically by the formulations of the drug. It's not even the physiology. So it is very complex profiles, and I doubt there is some guidance that I would offer in terms of more flexible or more adequate or correct kernel delays one over another. Basically, the approach is by trial and error, and then people, as you can see, try single distribution, gamma, Weibull. The differences between them, they have basically different tails depending on the shape factor. The gamma distribution, it has heavy tails. The Weibull allows you to regulate that, but that tail might not be the biggest part of the absorption data, so you might not be able to see that. And then if you have those double peaks, you will very likely use mixture models to account, one peak of the mixture for one peak of the absorption, and the second for the second. So flexibility is a name of the game for selecting of those kernel of distribution, and you can be creative there, and there is no no guidelines, and I doubt there will be. They're basically a very empirically based type of approaches. When it comes to identifiability, though, I mentioned that the absorption data alone almost always will lead you to a lack of identifiability of the scale parameter. Unless you have some IV data, you might have that, or you have multiple peak data, maybe you can have that as well. But if a single dose absorption data getting two parameters for the N distribution doesn't have to be weighable. Gamma distribution, same issue. If you have two parameters, shape and the scale or the of the rate, the rate is the parameter that is really practically hard to identify practically, because I haven't checked that, but when it comes to the structural identifiability, those parameters might be identifiable. I haven't proven that yet, but that is the mathematically identifiable parameter, although practically almost impossible to estimate. So my recommendation is to try to avoid estimating shape, sorry, the scale parameter, and then as I show you, I use my absorption rate as a scale for my distribution, and that resolves this problem with identifiability, does give us some mechanistically meaningful parameter for interpretation. So this is my approach to it.
Thank you. Next question. If the ODE and DDE implementations provide an equivalent description of the disposition process, and the DDE implementation has a longer runtime, what's the main practical advantage of using the DDE approach beyond simplifying the coding? For example, when early absorption data are sparse, can the DDE formulation improve model stability, reduce sensitivity to manually specified transit compartments, or provide a more robust characterization of the absorption delay?
So apart from that simplification of coding, which is the major driving motivation of this using that tool, I think I got this from your question, this issue that when you code the dosing events manually, it's not just a matter of inconvenience. It is the matter how your ODE solver handles such a code. So if the solver is really, if you sensitive to time inputs to the system, then I don't think this DDD approach will be numerically favorable. But if you have a solver that is, for instance, solve the differential equations with this change value of the integration step size, then when you input your delays manually, that part might be actually not so precisely enough. So if you are not careful with setting those the tolerance parameters for your solver, or the stiffness occurs and you don't have the stiff solver, then the DDE solvers, at least the one that I show you, definitely will be handling that better. They'll be stable. So that is my additional comment on additional advantages. If you don't really have good control of your ODE solver, please use the distributed delay solver, because people who introduced them, they had to take care of that issues already, and at least those dosing events are properly addressed then. So that would be the other aspects of using DDE models in terms of the numerical performance based on those manual ODE codes.
Well, great. I'd like to thank our speaker, Wojciech Krzyzanski, for an excellent presentation today. I'd also like to thank the attendees for their questions. Please check the ROSA website for upcoming webinars. These occur monthly. And at this point, I'd like to close today's webinar and thank everyone for attending. Have a nice day.